together. Does this look kind of familiar to you all? We were talking about the Hooke's Law Lab. So again, it's been a week. I know it's been a while, and I'm not expecting that you can repeat everything like verbatim right this moment, but I do want you to be able to kind of get back into the mindset. So we were talking last time about a spring. We put that spring or a mass on the spring. We had the forces, and then we graphed it. This is the Hooke's Law Lab that you may or may not have done. But just a friendly reminder that when we graph this, we graph displacement versus force, and we saw that as the force went up, the displacement went up, or vice versa. We saw that the slope of that is equal to this thing that we're calling the spring constant, okay? So it's the spring constant. It's how stiff or stretchy the spring is. The stiffer the spring, the greater the slope. The greater the slope, the higher the spring constant, okay? And then we took from that an opportunity to define spring potential energy. So we said that when we lifted the cheeseburger, we had a constant force. Force over distance was work. The area under the curve was the work done, or the change in gravitational potential energy, lifting that cheeseburger up. We said that when we're talking about a mass on a spring, that the force goes bigger and bigger and bigger and bigger and bigger as the displacement gets bigger and bigger. And as a result of that, the work is not constant. It's not a rectangle, but it's a triangle instead. So at the very end of class on Thursday, a week ago, we defined that the change in spring potential energy for an object that has elasticity is equal to 1/2 the spring constant times the displacement that it's moved from the equilibrium squared. Okay? And that's, I think, where we ended. Does that sound about right? Okay, so it's been a while since we've done that, but I just want to remind you. I want to remind you that you can use a spring for this, or you can also use like a rubber band, right? So we talked about that. So if I have my rubber band like this, and I apply a force backwards, so I'm applying a force this way, a force over a distance, change is work being done, which changes the spring potential energy, and therefore I'm gaining energy, okay? So you can imagine that you could put something, like if you had, a rubber band like this, you can use it like a little slingshot, right? Or you can use a spring to launch something. And that's the problem that we're going to start with today. So here is the situation that I want you to take a look at for the start of our day today. Oops, whoa, that's not what I wanted to do. Let me try that again. Insert a space here. Will it go? Nope. There, that'll be something. Ignore the 1 instead of an A or B. So here's the situation. My frog just got a new toy. It's a spring launcher. Whee! So he can be pushed back and then launched, kind of like a catapult, okay? He's sitting in the spring-loaded launcher, and it's ready to go, and it's at it has a spring constant of 56 newtons per meter. That means that it takes a force of 56 newtons to move it how much? 1 meter, okay? So it's kind of a lot of force, but that's to move it a whole meter. At this point, when he's set and ready to go, he's waiting for launch, he has 19 joules of elastic potential energy. Spring potential energy. Anytime you see the word elastic, you can transfer it for spring or vice versa. And I usually write this as PE sub S. Okay? The question says, how far from the equilibrium has the spring been compressed? So I want you to work on that problem. I do want to let you know that on your handy dandy equation sheet, you do have this equation. It's marked a little bit differently, and I apologize for that. It's marked E sub E. And I'm not sure, I think that maybe that's the way your book does it, but I can't remember for sure. But it's the 1/2 kx squared. So you might want to mark that on your equation sheet so you don't get confused. Okay, so on your equation sheet, it says E sub E for elastic. It's 1/2 kx squared. It's been a while since we've done physics. It really has, and I get that. I'm guessing most of you didn't do physics over your long weekend. I want you to solve this problem using the guess method. Givens, unknown, equation, stuff, and then solutions. What's that stuff? Substitution. There you go, and then solution. Once you've got part A, then try this other one. If the frog has a mass of 0.6 kilograms, how fast is he going to be going after he's launched? Take a couple minutes. Talk to your table mates. work on this problem together. You got it. All right, my friends. I feel as though some of you have decided that instead of trying these problems, you're just going to wait. Because Ms. Carbling's going to go through them, and that, you know what, honestly, I will. And that's fine. But I know from my experience as a student that trying things first, while it's not fun all the time, I will totally admit that, is always a better choice, because then you have something to jump off of, as opposed to feverishly writing down exactly what I do and I'm up here, because then it makes it a little bit harder to then transfer that the next time you do it, okay? But I am going to go through it, and if you haven't written it down yet, let's do it together. What are we going to start with? What's the very first thing we're going to write down when we're using the guess method? Indeed, let's do it. Who's got a given? Oh, it's frozen, so you can't see all my beautiful pink letters. Give me a given. What you got, Shad?
K is 56.
K is 56 newtons per meter, right? K is 56 newtons per meter. That means that literally, I just said this, it takes 56 newtons to push that spring back 1 meter. Okay, that's how stiff that spring is. What else do you know? Go, Ethan. It does. Again, I want to make sure that it makes sense to you so that you hear it now and you can process it. Elastic potential energy, spring potential energy mean the same thing. Okay? I write it as PE sub S, potential energy of a spring. On your equation sheet, it's written as E sub E, and I apologize if that's confusing. You can fix it on your equation sheet right now so that you know what it is. Okay? But PE sub S is 1/2 kx squared. All right. Any other givens that we have? No? Yes? No. What's our unknown? What is it? X. Yeah, how far did it go, right? How far is it pushed back? All right. GUE, we need an equation. Hey, look, the reason that I want you to write this down in this way again is not because I just bought stock in graphite, friends. It is not. The reason that I want you to do this is because we got lots of equations that we're trying to put together again. Kind of like we did with kinematics. It's not nearly as difficult, I don't think, but it's good to have this written down because now I know, oh, I need a PE sub S equation. Hey, look at that. I've got it. Okay? So I know that PE sub S is equal to 1/2 kx squared. Oops, I was getting really ahead of myself there. Sorry about that. 1/2 kx squared. And now I know, because I have it in my givens, that I need to solve that for x. So I'm going to do some algebra. You're going to do the algebra too. I get x is equal to the square root of 2 PE sub S over k. Do you guys agree with that? Is that okay? Okay. Does anybody want me to go through the steps of that? Looking for any sort of affirmative, otherwise I'm going to keep cruising. Are we okay? Okay. All right. Then we're going to plug in some numbers. If that really didn't make sense and you just don't want to tell me, or you're still processing or whatever, then let me know, because I'm happy to go through it anytime with you for sure. So that's 56 newtons per meter on the bottom. So 2 times 19 divided by 56, square root the whole thing. What do you get? What you get? Go for it. 0.824 meters. I'm just going to do 0.82 because I'm lazy. Oh, no, I'm writing the 4. My body was like, must write 4. All right. Is that big or little? Talking about a spring launcher for a frog. Think about that. This looks like a little number, right? It's not even 1. But it's not even 1 what? Meter. That means, guys, here's my frog. If he starts here, he's going to be pushed back this far. Are you with me? Okay? It's a pretty big launcher. Part of the reason I like this problem and part of the reason I don't change these numbers is so that you think about what this means. This is a pretty big launcher. It's okay, but I mean, like if you're thinking about a frog, that kind of makes sense. It's about the right size, right? Okay? But I just want you to kind of understand that we're not talking about 0.82 centimeters, right? It's like almost a meter. Ooh, that was loud. Okay? It's pretty big. This is supposed to be part B, but you know, It likes to pretend like it knows what it's doing. All right. This is where the meat of this problem is. Okay? I mentioned to you that you're going to have a quiz in 2 class periods, right? So not next time, but the time after, whenever that happens to be. If it's in April, whatever, it's going to be then. Okay? This is the problem that will appear, not this specific problem, but this kind of problem is the problem that will absolutely appear on that quiz. So I want to make sure that you understand it. It says if the frog has a mass of 0.6 kilograms, how fast is he going to be moving after the launch? It's a good question, right? I've got those givens, I guess, and then I guess I have a new unknown, and my new unknown is what? Velocity. Okay. So just staring at that, you might be like, I don't have an equation that has K, P sub S, and V in it. Like there's no equation for that. And I'm going to tell you right now that there is not an equation on your fancy orange equation sheet that will tell you how to do this. This is when you have to use physics. This is when you actually have to understand what's going on, and that's why I want to make sure you get this. I want you to think back to last week when we were together. Remember I had that ball that was hanging from that hook up there, right? And we pulled it back, and whose nose did it line up with? I can't remember now. Sam, how come you get to do all the fun stuff? Probably because she sits in that spot. I know, right?
I used to sit there.
What? I know, right? What is that about? Anyway, let's not lament about that. Let's just think about this again. So she was holding the ball up here. As she was holding it up here, just think back, because it's been a few days since we've done this. We talked about the energy. What kind of energy did it have? Potential. What kind of potential? Was it spring potential?
Mm-hmm.
No, it's a different kind of potential. What kind of potential was it? Gravitational potential? Yeah. Okay. And she let it go, and what happened? Let's think about it. It swung, right? And it swung and it fell. It went down, 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 which means that its gravitational potential went down. Do you remember this? We drew the picture. And as it came down here, it got really, really fast at the bottom, didn't it? Yeah. And then did it stop? No, of course not. What did it do? It started to gain potential energy. And what happened to its kinetic energy as that happened? It went down. You remember this? And then did it stop up here? No. What did it do now? It went back, right? And it hit Sam in the nose, or maybe probably didn't. Not quite, which is good because she would have been sad. Okay? But it went back and forth and back and forth. And the reason that we did that was because we were talking about what principle? There's one rule that is true in all of science, friends. Look back in your notes if you don't remember. There's one rule that is true in all of science. It is the rule of what? Conservation of energy. This is it. This is it. Conservation of energy. It says in a closed system. I would write this down again because my guess is that you didn't all have that in the front of your head before. It's been a while. The more times you write it down, the more times you hear it, the better it sticks. You know that they've done research and it says you have to write things down 3 times in order for them to stick, right? Okay, so this is number 2. So here it comes. In a closed system, that means no outside forces acting, okay? The total energy remains the same. So let's think about my frog. Let's think about the launcher. Shahad, I'm going to have you hold my launcher. Can you do that for me? You just have to just sit there and hold that. Perfect. She's like, I don't know what that means to hold your launcher in your hand. Give me a meter stick. Yes, there you go. Okay. So here he is. I'm going to set him right here on the launcher, right? And then I'm going to apply a force. Are you with me there? Over a distance. There's a spring here. And it's going to be harder and harder and harder and harder to push. And then I'm going to lock it there. So now he's here. So I applied a force over a distance. What was I doing? I was doing work, right? And as I was doing work, I was adding energy to the system. Are you with me there? Okay, hold that for just a second. You just keep doing your thing, okay? That was not a closed system because I was adding energy to the system. You with me there? Work is being done, adding energy. Now, let me tell you a secret. If the system included me and that pasta that I ate for lunch, that chemical energy, that stored chemical potential energy inside my body, then my chemical energy is now turning into potential energy. Are you with me there? I am losing energy, but the frog is gaining energy. And if we're a system together, then instead of me doing work, it's just conserved energy. It's just chemical energy. Chemical energy is turning into potential energy. Okay, we're going to ignore that part though. That was just, an aside because it's interesting. All right, so here we go. So now the frog is back here at 82 centimeters-ish. I don't know if that's really 82 centimeters, but we're going to pretend. Is it about?
Yeah. No, it's in the back.
Oh, over here further?
Yeah.
Okay, there he is. All right, so he's that back there. So now you have to imagine, because this part I don't have like the actual spring, but this spring is pushed all the way back here. So it's really tight. There's a lot of energy. How much energy is in there? 19 joules. You with me there? 19 joules of elastic potential energy are in there. And then I'm going to flip the switch so that that spring can go back to normal. What's going to happen to him, Madeline? Ding, right? A little projectile motion problem again. You with me? But I don't really care how far he's going to go. We're not going to do that part. I just want to know right when he gets here. So now he's been released. How fast is he going? Does that question make sense to you? Do you understand what I'm asking? Okay, thank you for being my launcher. I appreciate that. All right. So how are we going to solve this question? This is what I would encourage you to do. Whenever I'm using conservation of energy, the first question I'm going to ask myself is what types of energy are involved? Well, what types of energy do we know about? We know about gravitational potential energy. We know about kinetic energy. We know about spring potential energy. Do we know about any other kinds of energy yet? We're going to do one more today, but I think those are the three we know about. Of those three, which ones are involved? It might be one, it might be two, it might be three. Yeah.
Potential.
Which kind of potential?
The one with the S.
The one with the S, absolutely. So spring potential energy is involved. Kinetic energy is involved. Is gravitational potential energy involved? We don't need it to be involved. Remember, just a little friendly reminder, because again, it's been a little while, that potential energy gravitational is mgh. So if his height doesn't change, then the gravitational potential energy doesn't change. And the way that Shahad was so nicely holding that launcher was all flat, wasn't it? So that whole time, the height wasn't changing. You could include it if you wanted. Let's not, though. It's not, because we don't have to. So we just got kinetic and spring potential. And then step 2, this is where the equation comes in, because I'm not going to give you a fancy little chart for this because I don't think you need it. What I think you need to understand is that conservation of energy is true. So that means that the total energy at the beginning has to equal the total energy at the end. Every single time. What types of energy are involved? Total energy at the beginning equals total energy at the end. So now we're just going to write it out. So we've got kinetic energy at the beginning plus spring potential energy at the beginning has to equal kinetic energy at the end plus spring potential energy at the end. Before he's launched, is he moving? Before he's launched, I push him back, and then he's just sitting there. He's just waiting. Okay, it's like when you're on a roller coaster and you're like waiting for that like start. You know what I'm talking about? Just wait for it, wait for it, wait for it. Is he moving? If he's not moving, what kind of energy does he not have? Okay, Kinetic. There's no kinetic energy. There's none because he's not moving. And at the end, remember the spring is released. The spring is back at its normal length. What do we not have anymore at the end? Spring potential, right? How much spring potential did we start with? 19 joules. Ooh, kinetic energy equation. Do you remember what it was? Or check your orange sheet. Those are two good options. What is it? 1/2 mv squared. Hey, they told us that the mass was, what was it, 0.6 kilograms? Can you solve that for velocity? So V is equal to the square root of 2 P sub S over M, square root of 2 times 19 joules over 0.6 kilograms. Whoa. How fast is he going? Everybody should do the math. Don't trust those people around you in this case. I want to make sure you know how to do it. Because 2 days from now, 2 school days from now, you will have the opportunity to do this and show me you know how to do it, right? So I want to make sure that you know what you're doing so that you can solve these problems. Check with your table mates. If you got an answer, check with your table mates and see if they got the same answer. How fast is he going? Megan, did you get an answer?
Yeah.
What did you get?
7.953.
I'll do 7.96. Resist the urge to go to the thousandths place. What are the units? Meters per second. So he's going pretty fast coming out of that little launcher. Yeah. How are we doing? We okay?
Oh.
Ish. Question? At the beginning of the what? Day? Oh. Work. Force times distance. We're going to do it again. I'm going to go do a demo way at the back of this table. Are you guys okay with that? Yeah. Okay. Nope, this one back here. Because I figure most of you can see this and I stand back here, right? I use lots of high-tech things for my demos and stuff. I like the Kleenex box. All right. So, let's take a look at the Kleenex box. If we call H equals 0 the table, does that Kleenex box have any energy? No kinetic. No gravitational potential. I call this gravitational potential is 0, right? H equals 0. No spring potential, because there are no springs involved. You with me? I'm going to apply force. You ready? A force over a distance. I'm going to do what to it? What am I doing? Work. And by doing work, I'm changing the amount of energy it has. You with me there? So I'm giving it energy. The energy is coming from me. Remember? The energy is coming from me, from the pasta I ate for lunch. But I'm just going to call me part of the outside world. And so really it's just the Kleenex box. The Kleenex box is going to get some what kind of energy? Let's watch. What kind of energy did I give it? I gave it some kinetic energy. With me there? Yeah, absolutely I did. Now, what did you notice about the Kleenex box though? You said it had kinetic energy. Does it still have kinetic energy? Energy has to be conserved. Within a closed system, no outside force is acting. The total amount of energy should be the same.
But you did all.
I did, but I'm saying I gave it some energy so that it was moving at a kinetic energy. But something else is acting on it, isn't it?
Friction.
You with me there? Friction is also acting on the system. Okay? So I'm going to apply a force. I'm going to give it some energy. It's got energy. Woo! Okay. Yes. Okay? And friction acted enough such that it stopped it. It was a force applied over a distance in the other direction. Okay? Now, if I do work, I'm giving the box some energy. Can that energy, like, where did the energy go?
There.
It went where?
It's thermal because of friction.
It's thermal energy. So that energy that it had in kinetic energy is then being converted. Are you with them there? Are we okay? It's being converted to thermal energy. It's being converted to heat. Okay, not a lot of heat, but a little bit of heat, enough to get rid of that. So I'll tell you, last period I did this, and I explained that, I talked them through it, and then I walked back up to the front, and I heard this mumbling of, I have no idea what she just said. And so I'm hoping that you all aren't feeling that way, but if you are, I've got a couple minutes to try and get you where I want you to go. So come with me here. We're going to talk about thermal energy really quickly. Here it comes. So go ahead and draw yourself a Kleenex box. And draw yourself a table. Actually, I'm going to make my table a little smaller. I'm going to do 2 parts in one story. Whoa! Smaller table. There we go. So step 1, Miss K is going to apply a force over a distance, okay? Which means that I'm doing work on the Kleenex box. And because I've done work on the Kleenex box, I am changing the amount of energy that the Kleenex box has. So then the box has kinetic energy. So here is my force. I'm applying a force over some distance. Okay? And in doing so, my box now has kinetic energy. Okay? We remember that work is equal to force times distance. This is the very first thing that we did in this unit. Okay? And then we also said that work is equal to the change in this case, kinetic energy. So far, so good? The second half of this story is that the table applies a force to the box. Applies a force to the box. Okay, a force over a distance. So now we're going to draw the Kleenex box, and it starts off moving. So here's the table. It's kind of the second half of the story here. Which way does the force push or pull on the box? To the left. Why?
Because it's a friction force, so it's going the opposite direction as the wax.
Yeah. It's a frictional force, and so it goes the opposite direction of the box's motion, right? Yeah. So there's a force in this direction over a distance, and in doing so, the box loses the kinetic energy. No more kinetic energy. But that energy, instead of being kinetic now, has now escaped into the rest of the world as heat. Okay? Okay. So we say, I'm going to just clear this up here. So the table applies the force of the box, does work, on the box, the kinetic energy turns into thermal energy, which is also known as heat. Okay. Work is done. This is the force of friction times the distance, okay, is equal to, I'm going to call this E sub TH for thermal energy. Okay. How are we doing there? Are we okay? So far, so good? Okay. We have 1 minute. I'm not going to start the next problem because I don't want to confuse you. I am going to let you know. Is it okay if I click to the front page again? Is that all right? I am going to let you know that if you have not yet done these problems, I would strongly recommend that you do them. If you have not yet started these, which I'm expecting you haven't, these are the homework for tomorrow and or the next time I see you, okay, whenever that is. If you don't do these problems, it's going to be really hard for me to get ready for the quiz, okay? Please do that homework before I see you next time so that we can have something to talk about then. Take a picture. And it's National Compliment Day. Thank you all for your hard work today. You did a great job. And I'm not just saying that because it's National Compliment Day.
Monday.
I don't know. I think that the next few
Wednesday?